Hello and welcome back to Proving Triangles Congruent. Today we're going to prove triangles congruent using angle side angle and angle angle side. So to start off, what is angle side angle? Okay, the definition is if two angles and the included side of one triangle are congruent to two angles and an included side of another triangle, then the triangles are congruent. So we're going to start off. We're just going to use our picture here. If angle A is congruent to angle D, that's our first angle. If side AB is congruent to side DE, that's our side. So we have angle side, last angle. If angle B is congruent to angle E, then we have a pair of congruent triangles. So triangle ABC is congruent to triangle DEF. Okay, so we went angle side angle. We're going to start off with a sample proof. I'm going to do the first one with you. You can do the second one on your own. Here's our given statements. Now remember, the given statements are always written first in our two-column proof. So they tell us that SQ bisects angle RQT and angle RST. Now, if you haven't figured this out already, if you see bisects, okay, we're going to come over here to our reasons that angles are congruent. If you see bisects, you will always use the definition of angle bisector, because a bisector will create two congruent angles. Okay, that's what the definition is of a bisector. So we have that. We have bisects angle RQT. So RQT is this big one right here. So if I'm to bisect RQT, I'm going to get a congruent side here. I'm sorry, a congruent angle. I'm going to get one right here as well. Okay. We're going to do the same thing with angle RST. RST, we start at R, we go to S, and we end at T. Talking about this big angle right here. We're going to bisect that as well. I need two arc marks because this is a different angle than RQT. Okay, so now we have that. Our goal is to prove that triangle QRS is congruent to triangle QTS. Okay, so now we're going to start with our first row here. Okay, so SQ bisects angle RQT and angle RST. That's given to us. The second row, angle RQS is congruent to angle TQS. So where is RQS? So we start at R, we go to Q, and then S. So that's that guy that we just created right here. That was the first thing that we did. So RQS is congruent to TQS. Okay, we know that this is true because of the definition of angle bisector. Okay, so they gave us bisects. We use definition of angle bisector. Line 3, angle RSQ. Where's that at? RSQ. Okay, that's the second one that we created from what they gave to us. So RSQ is congruent to angle TSQ. Here's TSQ. So these two angles are congruent, again, because of the definition of angle bisector. Okay, so again, anytime that you see bisects, use the definition of angle bisector. Okay, and put that in bubbles because it's that important. Moving on. QS is congruent to QS. So where's QS? QS is a side. It's right here. Notice that both of the triangles share it. Okay, so in blue, I'm going to do the triangle on the bottom. In red, I'm going to do the triangle on the top. Both the bottom and the top share side QS. And we can say that QS is congruent to QS because of the reflexive property. Remember, reflexive property says that a side is congruent to itself. Side is congruent to itself. So here, we have reflexive property. Then lastly, line 5. Line 5 is what we're trying to prove. Triangle QRS is congruent to triangle QTS. Notice we went angle, side. Okay. Now just because we went angle, side in our two-column proof does not mean that we used angle, side to prove it. Okay, we got to take a look at our picture. So we went angle. Here's the included side that's between the other set of angles. So we got one pair of congruent angles, another pair of congruent angles, and the side that is between them, that's our included side from up here. Okay, that is side QS. We use angle, side, angle for this proof. Okay, just a quick hint for you. If you see parallel, okay, the two lines up and down mean parallel. If you see parallel in your given statements, you're going to use alternate interior, alternate exterior, or corresponding angles. Notice it says you must have parallel lines. Okay, so if you see parallel, you're going to use one of these three somewhere in your proof. Okay. And flip the page. We're going to talk about angle, side next. Here's the definition. If two angles in a non-included side of one triangle are congruent to two angles in a non-included side of another triangle, then the triangles are included. So we're going to do the same thing. We're going to take a look at our picture here, and we're just going to go through our congruency statements and then finally write how these two triangles are congruent. So first, if angle A is congruent to angle D and angle B is congruent to angle E and side BC is congruent to side EF, then triangle ABC is congruent to triangle DEF. Here's something important. Non-included means a side opposite of the angles. Okay, so really, I mean, we could have side BC, that's opposite of these two, or you could also have side AC, that's opposite as well. Okay, what we don't want is the side in between the angles, which would be side AB or side DE. Okay, since we already did a proof with bisects, okay, we still got midpoint left. I'm going to go ahead and flip the page over. We're actually going to do one with parallel and midpoint. So, remember the first thing we do is we fill in the given columns. So, I'm just going to write what they gave to us until we don't have anything left to do. Okay, so angle ABC is congruent to angle CED. That's our first given statement. I'm also going to draw that on the picture over here. ABC, start at A, go to B, here C. Okay, so that bad boy is congruent to angle CED. So those two angles right there are congruent. Next up, side AB is parallel to side CE. So it's at AB. I'm just going to draw nice arrow just like that. Do the same thing for CE. These arrows, black arrows, mean parallel. So these two things are given to us. Remember what we said about parallel. If they're parallel, we're going to use alternate interior, alternate exterior, or corresponding. So we're going to have that somewhere in our proof as well. Next up, C is the midpoint of AD. Anytime that you see midpoints, you will use the definition of midpoint in your proof, just like bisect. And before we do that, we're going to go ahead and label that on our picture. C is the midpoint of AD. So here's side AD. C is the midpoint. What does that mean? Here's the definition of midpoint. A midpoint will create two congruent sides. Midpoint creates two congruent sides. So that means that on the left, AC, that side is congruent to CD, which is on the right. Okay? Now, where do we go from here? Well, first thing that we can do is we can use our definition of midpoint since it's on line 3. Okay, so we created AC is congruent to CD. And that was the definition of midpoint. We have not used parallel, so that's going to have to go on line 5 somewhere. And then line 6 is what we're trying to prove. Remember, what you're trying to prove always goes last. So triangle ABC is congruent to triangle CED. That is what we are trying to prove. So we're going to leave this side blank, the right side. Okay, we're going to come back to parallel. We have one angle, one side. We need another angle somewhere. So AB is parallel to CE. Now, if I take AD right here and I extend it just like this on both sides, okay, we could consider this a transversal line that cuts two parallel lines. So when that happens, I have 4 different angles that it creates. I got one here, here, and then if this is extended, we got one down here and there. So I'm just going to say 1, 2, 3, 4. It also happens right here as well. So I have 1, 2, 3, and 4. Now, remember we said that if there's parallel lines, we can have alternate interior, alternate exterior, or corresponding. All 3 of these are congruent to each other. Alternate interior have to be on different sides of the line. Okay? So since we do not have a pair that are on opposite sides of each other, we can't use alternate in any way. So that means that we have to use corresponding somehow. Corresponding, we've talked about in our first congruent triangles video. We also talked about with parallel lines being cut by transversals. Corresponding means the same position. Same side, same position. So we need 2 angles that are in the same position on both of these triangles. So if you just look at our numbers that we labeled, 1, 2, 3, and 4, number 2 happens to be in both triangles. Okay, so since number 2 is in both triangles, that means that the 2's are congruent. Another way that you could think of it, okay, if we go top left, top right, bottom left, bottom right, 2 is in the top right position out of these 4 angles, the top right. Right here, this angle right here, it is also in the top right position. So they're both in the same position no matter how you look at it. So we're going to say that angle BAC AC is congruent to angle ECD. And we know that they're congruent because they're corresponding angles. Okay. Last line, we got this number 6 to fill in on the reason side. What is our reason that these two triangles are congruent? Okay, notice that our side is opposite of these two angles. So we have angle, angle, side. So we put AAS. And there's our proof.